Alright, let's start. I'm David Reeb. I'm covering today for Professor Werner. He's away at a workshop. And today we're gonna look at the geometry of the set of positive semi-definite matrices, or the geometry of the set of quantum states. Basically, I think we started with this last time, but I will recap everything. So in the previous section, we introduced the notion of positive semi-definite operator. So this is an operator acting on a Hilbert space, so a map from the Hilbert space to the Hilbert space, bounded linear map. And such an operator is called positive, or I prefer actually the term positive semi-definite. If and only if, the definition was kind of that the operator has to be Hermitian, and the spectrum cannot contain any negative values. So the spectrum has to be contained in the positive real line. The fact that the operator is Hermitian guarantees that the spectrum is completely real, and positive semi-definite means that the spectrum cannot contain any negative eigenvalues or continuous spectrum. And we showed that this is equivalent to the fact that the inner product, if you take the inner product, so if you sandwich A between two vectors of the Hilbert space, this will always be non-negative. So this is a very useful definition. It also turns out that this is equivalent to the statement that A can be written as a square of an operator. So Hermitian adjoint of some operator times the operator. And today I will be looking at the set of positive semi-definite operators, mainly, or sets that are derived from this, and all of this can be phrased in the language of convex sets and convex cones. So I will introduce a bit of this notion and then sometimes come back to the set of positive semi-definite operators. So a subset of a vector space. So a subset of a vector space and so this has to be a vector space over the real numbers. Such a set is called convex. Convex, if, I suppose everyone knows the definition, so if for every real number between 0 and 1, and for every pair of elements of the set V1 and V2 of this set, it also holds that the interpolation of these 2 points, lambda V1 plus 1 minus lambda V2, is an element of the set. So this is what is called a convex set, if this holds. So this means that we have a vector space and we have the set S. This means that the line between any 2 points, V1, V2, is fully contained within this set. All right. So turns out that many sets in quantum information theory are convex sets. So a lot of what we are doing in this semester can be phrased in terms of convex sets. If you have a convex set, so an element of a convex set is called an extreme point. If the following property holds, that if you want to write this point V as an average of 2 other points, so as a real average, as a true average of 2 other points, then actually the 2 other points have to agree. For example, if you take, if the boundary is like curved, if the boundary of the set is curved, and you have a point V on the boundary, then the only way to decompose this point as a convex combination of two other points is, I mean, if you take any 2 points which are inside S, you will always miss. You will miss the point B. Right? So this makes. I hope this makes sense. So this point V would be an extreme point. And the formal definition is the following: if the following statement, so lambda V1 plus 1 minus lambda V2 equals V for V1 and V2 element of the convex set, and lambda reading the interior of the interval between 0 and 1. So you would like to write V as an average of the 2 points where the 2 weights are not 0. So if a representation like this implies that V1 equals V2, and this has to then to be equal to the point V. Any questions about this? So I guess this makes sense. Now let me define another notion for a convex set, namely the phase of a convex set. So take as an example the following convex set. So this would be the set S. Subset of the 2-dimensional real vector space, which is the blackboard. So this set is convex, and the extreme points would be this point and all points on that boundary. So we can have colors. Maybe not, but so the extreme points of the convex set are, I mean, this point. Tilde, tilde, and this arc. All right. The points which are on a straight line, they can be decomposed into a convex decomposition of 2 other points. For example, if I take this one here, then one can write this point, if we call this here V hat, then this point would be 1/2 V tilde plus 1/2 V hat. So this is not an extreme point, however it lies on the boundary of the set. Right? And some convex sets have straight boundaries, and they are called phases. So another definition. A subset of a convex set is called a phase. Phase if so if whenever you want to decompose a point on the phase into a convex decomposition of other points, then the other points lie in the phase as well. So if you take a point V from S and you decompose it into 2 other points, like a true convex composition which has non-zero coefficients, and V1, V2 in the set, if this here implies that V1 and V2 are an element of the phase as well. Does this make sense? Okay. let's take an example.
Write a little bit larger.
Sure. I will try to. If it's small, you should tell me again. So let's take an example. So let's take the set of probability distributions on 3 elements. Okay, I will try to write larger. Probability distribution on the set 1, 2, and 3. So this is a subset of the real 3-dimensional vector space, and this is the set of, if I write probability distributions as vectors, then this is the following set of vectors P1, P2, P3, elements of R3, such that probabilities have to be positive, and they have to add up to 1. P2 plus P3 is equal to 1. So this is the set of probability distributions on 3 items. And so this is a convex set. If you take 2 vectors with only positive entries, and you take a positive linear combination, like with positive coefficients, then all entries will remain positive, or at least non-negative. And if you take 2 vectors where the entries add up to 1, and you take a convex combination like 30% times one vector plus 70% times the second vector, they will still add up to 1, because the coefficients add up to 1. So this is a convex set. And one can visualize it as follows. So it turns out that this is only a 2-dimensional convex set. It's a subset of the 3-dimensional vector space, but we have one equality constraint. So one way to visualize this set is we look at at a plane in the 3-dimensional real vector space, and then it turns out that this set is equal to basically a triangle, and the corners are these points. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is S, and that's also called the probability simplex in 3 dimensions. Probability simplex in 3 dimensions. Okay, what are the extreme points of this set? Does anyone want to answer yes?
The corners.
So there are 3 extreme points. That's right. And the faces? I guess it's quite obvious, okay? So these are the three faces of the set. So these are the extreme points. So it's called, I'm not sure if we will use this notion, but it's called a simplex for the following reason. So this also has an abstract definition. The definition of a simplex is that if you take a point in the interior, or no, if you take any point in the set, and you would like to write it as a convex combination, so this means that, let me write it down, for every element of the convex set, like for this point, there exists a unique decomposition. There exists lambda 1, lambda 2, lambda 3, unique with V equals sum over I, lambda I, Vi, these are extreme points. So for a simplex, every point can be only uniquely decomposed into a convex decomposition of extreme points. It's quite easy to see, so if you would like to write a point like this, as a convex sum of these points, it would be P1 times this vector plus P2 times this vector plus P3 times this one. There is no other way. Are there questions up to this point, or is this like too trivial? Okay, let's look at the set of positive semidefinite matrices. So this was just some warm up. So let's define C to be the set of positive semidefinite matrices. So this is the set of positive semidefinite matrices. It turns out that this is a real vector space, but not a complex vector space. Well, this is a sub. How should I say this? Well, okay, it's just a set, and this is convex. Since A greater or equal than 0 and lambda greater or equal than 0 implies that lambda A is greater or equal than 0, and lambda A greater or equal than 0 and 1 minus lambda B greater than 0 implies that also the sum of both operators is greater or equal than 0. So So this is a convex set. The set also has another property which normal convex sets don't have. And so this is this property. That positive multiples of an element are again in the set. So this is not shared by all convex set. Not shared by all convex sets. So kind of what this property means is that, so if we take a vector space V, and so for any element of this set C, also all elements on the ray that, so if we take an element A and we take the positive ray that is spanned by this element A, this is again an element of the set. And so this holds for every element in the set. And also the sum, I mean, since it's a convex set, also everything in between these two rays has to be in the set. So, and maybe there are more rays, kind of like this. Alright, so a convex set which has this property is called a convex cone. It's called a convex cone. Like in German, this would be cylinder, which it looks like a cylinder. Since C is convex set, and V element C, lambda greater or equal than 0, no constraint on the size like 1, implies that lambda times V is again an element of the set. Alright, so the set of positive semidefinite operators forms a convex cone, basically. There is a generic construction to relate convex cones and convex sets. So this is a generalization of what we also encounter in quantum mechanics, and this is the following. So if we take a convex cone and we cut the cone by a hyperplane. So for example like this, and we look at the intersection. At the intersection. So this would be a hyperplane. Then the intersection is called a base of the cone, at least under some circumstances. So we shouldn't take a hyperplane which fully intersects the cone. Okay. So the kind of the condition is that this is then called a base of the cone, base B. So the definition is the following: a base B of a cone is the intersection of C with a hyperplane such that the hyperplane really intersects the whole cone. So it shouldn't be, for example, this hyperplane, which is parallel to the side of the cone, because no point on this ray would be an element of that hyperplane that I've chosen. So the hyperplane has to be chosen correctly, namely in such a way that the cone C is equal to lambda times V for all positive elements lambda. So every element of the cone, you should be able to write it as a positive constant times an element of the base, or at least a non-negative constant, such that you also can get the origin. So in this case, that's what's called a base of a cone. And so an example of this is when we don't look at just positive semidefinite operators, but at quantum states. So let me make an example. S equals the set of quantum states, on a Hilbert space H, so this is the set of, well, it's not a subset of the set of bounded operators. It's just, I mean, quantum states have to be trace class operators, namely for the reason that, I mean, bounded operators can be positive, but for quantum states we require that their trace is equal to 1, so in particular finite. So they have to, I mean, this condition automatically implies that quantum states have to be trace class operators. So the set of quantum states is exactly of this structure. It is the intersection of the positive semi-definite cone with a hyperplane. And in this case, it's the hyperplane of all states that have trace 1. So this is one linear condition. It's the equation of a hyperplane in that linear space. The space of bounded operators or the space of trace class operators. All right. So many notions in quantum mechanics are special instances of general notions in convex geometry. So for a general cone and a general base, this would be just any linear functional of which you require that it should be equal to 1. So this hyperplane would be the set of all operators A for which some linear functional evaluates to 1. And I mean, it should still have the property that it fully intersects the cone, so that the cone is spanned by the base, basically. So some notions that we define for general convex sets, they don't really make so much sense for convex cones. For example, the property of being an extreme point, I mean, this is a very important notion for convex sets, and we will talk about this in a second for some convex sets, but this is not the right notion somehow for convex cones, because convex cones only have a unique, I mean, I guess this is generally true. So a convex cone has only one extreme point, and this is the origin. I mean, the origin, because you can always choose lambda equal to 0, the origin is an element of every convex cone, and this turns out to be the only extreme point, because if you take any other point on a ray, so on one of these rays, then you can write it as a convex combination of two other points on the same ray, so of the same set. So the notion of an extreme point is not so, it's not the right notion for a convex cone. Instead, we should either ask about extreme points of a base of the cone. So if we restrict the cone in such a way that we cannot take arbitrary multiples anymore, or instead we should look at a notion that is called extreme rays, and this is the following. Extreme points, not so useful for convex cones. Instead, the right notion is extreme ray. So, and this is the following. to define this notion, one needs to relate. One can also do it the other way. So, a matrix A in this cone C. This is set to lie on an extreme ray. So the extreme ray is defined to be this set, all positive multiples of that operator, if zero smaller or equal than B, smaller or equal than A, implies array. So generally, array is called a set which can be obtained by taking an element of the cone and taking all positive multiples. So now I don't really know how to draw it here. For example, this here would be array of the cone. This here as well, and this here as well. And an array is called an extremal array if you take a point. A point is said to lie on an extremal array if you take any point that is smaller, like in the positive semi-definite order. How do we say about this definition? Of course, the definition of this here is that 0 is smaller than A minus B. So this means that A minus B is in the cone. So whenever you to the case that A equals B1 plus B2 if this implies So that's another way to say it. A point is said to lie on an extreme ray whenever if you want to write this point as a sum of two other points of the cone. These two other points, B1 and B2, have to, lie automatically on the same ray. So this is, for example, true for this point. If you want to write this point here as a sum of two other elements of the cone, then, let me make an example here. So, if we take, for example, this point A, we can write it as this element plus this element. Because, the sum of these two elements is just go along this one and go along this one, and you end up at A. So it's maybe more like this. Right? So this point in the interior can be written as a sum of two elements that don't lie in the same direction. But this is not possible, for example, for this element. If you would like to write this A here as a sum of two elements of the cone. I mean, you can go into the interior of the cone, but then this arrow doesn't lie in the cone. I mean, it points out of the cone. I hope you can see it. So the only way to write this here as a sum of two elements is you take two elements which are already on the same ray. So that is the right definition for a convex cone. I hope this is clear, or please ask questions. So maybe now we are switching to looking at what are the extreme points of sets that are important in quantum mechanics. So it's kind of now, there's a bunch of examples following up on these definitions with like more concrete material. Extreme rays and extremal points of quantum mechanical sets. Namely, to clarify what are the extremal rays of the convex cone of positive semi-definite operators. So the extremal rays of the convex cone of positive semi-definite operators on a Hilbert space are exactly the sets take all multiples of a rank 1 positive semi-definite operator, where lambda is greater or equal than 0. So, and you get one such set for each element of the vector space. So we have to show two different directions. Namely, we take a point on an extremal ray, and then we have to show that this point is a multiple of a pure state. And secondly, we have to show that every multiple of a pure state lies on an extremal ray. So let's say A. Let A element of C be on an extremal ray. On an extremal ray. Now we would like to show that A can be written in this form for some lambda. So what do we want to verify? we try to write A as a sum of two other elements of the cone, and would like to conclude that these two other elements are multiples of A. Now, what do I like to do? Let's do the proof in another way. So I want to show that all extremal points look like this. So how I'm going to do this is to say that if we have an operator which is not, if we have a positive operator which is not a multiple of a pure state, then it won't be, won't lie on an extremal array. So let A be not equal to of this form, but A should be an element of this cone. That means A is greater or equal than 0. So what does this mean? A greater or equal than 0 means so since A is greater or equal than 0, we can write A is equal to a unitary times a diagonal operator times a unitary star by the spectral theorem. So this is a unitary, and this is a diagonal operator. So Professor Werner called this a multiplication operator, which has only diagonal entries on its diagonal. Diagonal operator with non-negative diagonal. So this means that D is equal to D1, D2, all operators of this form, all operators of this form are rank 1 operators. So, these operators have the property that only one of the eigenvalues is non-zero. At most, one of the eigenvalues is non-zero. So, because A does not equal because we assume that A does not equal an operator of this form, we know that at least two elements on the diagonal are non-zero. So, since A cannot be written in this rank 1 form, we have that A has to have at least two non-zero diagonal entries. If it had only one non-zero, if this diagonal matrix had only one non-zero diagonal entry, then it would be immediately of this form. It would be a rank 1 state with a unitary still a rank 1 state. We have that at least two of the diagonal entries are not equal to 0. And all of these DIs are non-negative because the operator is non-negative. Okay? So if A is not of this form, we can write it in the following way. without loss of generality, these are the first two elements of this vector. Then we can write it in this form. So if A would not be of this form, we could write A as a sum of, we just decompose this, this diagonal matrix in an obvious way into an operator and another operator. Both of them are positive, bigger or equal than 0, and not equal to 0. So I define this here as A1, this here as the operator A2. So both of them are positive semi-definite, so they are again elements of the cone. And one can easily see that these two operators are not multiples of this one here. Right? And we have, for example, A1 is not equal to some positive constant or some any number times A. I think this is quite obvious because if this operator A1 would be a multiple of this operator, then for example we would have to have that mu times D2 is equal to 0 and mu times D1 is equal to D1. So one of them implies that mu equal to 0, one of them implies that mu equal to 1. So if A is not of this form, then A can be written as a sum of two elements of the convex cone, so A is not an extremal array. A does not lie So now we have shown that if A lies on an extremal, if A lies on an extremal array, then it must be of this form. So we have learned that all extremal arrays of C are of the form what remains to be shown is that all of these sets are actually extremal arrays. So it remains to show all these sets are in fact extremal arrays. So how are we showing this? So let A be equal, let A be an element of such a set, and A1 plus A2 is equal to A. So we want to write this element as a sum of two elements of the set. So this means, for example, that A1 plus a positive semi-definite operator has to be equal to A. So this implies that A1 is less or equal than A. I mean, the difference between A and A1 is a positive semi-definite operator. So last time, in the last lecture, so again, this is equal to lambda psi psi. So in the last lecture we showed that this implies, so this is a projector. This is it's a Hermitian operator which squares to itself. So in the last lecture we showed that this implies that if we sandwich everything with the projector again, so psi, we take the projector times A1 times the projector, then this again has to be smaller or equal than how did we show this? I guess we have to again prove it by diagonalizing both sides, essentially. I don't think it works like this. Yeah. I guess what we showed in the last lecture is that if an operator is smaller or equal than a projection, then the operator commutes with the projection. Or in fact, so let's call this a projector equal to P. What was shown in the last lecture, these were some properties of the positive semi-definite ordering. So last lecture, we showed that in this case, P times A1 times P is actually equal to A1. So if an operator is smaller than a projector, then the support of the operator has to be actually contained in the projector, equal to A1. So this was a statement that was shown as some implication last time. So this means that A1 is equal to P times A1 times P. So, and the projector that that we have in this case is psi A1 psi. So this is now just a number. In fact, it's even a real number because A1 is Hermitian. So this is equal to some number times psi psi. So what we have shown is that if we want to decompose an operator A of this form into a sum of two positive operators, then these two positive operators necessarily are of the same form. So if we define this here as mu, for example, then this is equal to mu times psi psi. So each of the two terms in the sum is of the same form. So this was our definition for A to be on an extremal array. So this is of the same form. So this means that A was on an extremal array. Sorry for the confusion. Does this make sense? All right. So a consequence of this is, so now we have computed the extremal rays of the cone of positive semi-definite operators. So the set of quantum states. So the set of density operators. So let me write it down again. This is the set of trace class operators on a Hilbert space. Which are positive semi-definite and have trace equal to 1. So this is, as I said before, this is a base of the cone C. It's a base of the cone of positive semi-definite operators, and once we have computed all the extremal rays of this cone, which we have now done, we can immediately say what the extremal points of the set of density operators are. So as a consequence, the extremal set D of density operators is, so the set of extremal points of D is the set of ket bra vectors where psi is an element of the Hilbert space, and the trace of psi psi is equal to 1. It has to be an element, of course, of that set, of that base. So I think we talked about this last Thursday, that this is just the inner product of psi with itself. Alright, so the extremal points of the set of density operators are all operators of this form, and they are, I mean, of course, the so-called pure states. the set of quantum states is one of the important sets. Another very important set, or one that will come up more often, is the set of effect operators. And maybe if I have time later, I will talk a little bit about POVMs. So remember, there was this picture. So there was a quantum state was prepared, rho, and then maybe it goes through some channel. So preparation. Described by a density operator rho, maybe undergoes some quantum evolution, and then in the end of our experiments we usually perform a measurement. And measurements are measurement, or like compute an average or something like this, and this is described by measurement operators, and some basic measurement operators are the so-called effect operators. I will maybe later say what a POVM is. So basic measurement operators. So this is the set of effects. So this is the set of operators that are bounded operators on the Hilbert space, which describe our quantum systems. And so again, these are positive semi-definite, but smaller or equal than the identity operator. So this is kind of the identity matrix or the identity operator. So this is called the set of effect operators. And the F are also called effects. So these are positive semi-definite operators, and the eigenvalues are between 0 and 1. So it's again a convex set, of course. If two operators are positive semi-definite, also their convex sum will be positive semi-definite. If two operators are smaller than the identity, then their convex sum will also be smaller than the identity, because the convex sum of twice the I think it's quite obvious. So this is a convex set. It's not a convex cone though, because if you take an operator f and multiply it by a large constant, it will usually be larger than the identity operator at some point. So this is not a convex cone. So, and the theorem about them is that the extremal elements of the effect operators are in fact the projection operators. So this is the set of projection operators. So the Hermitian elements of that bounded set, which square to themselves. So when we later talk about POVMs, like about real measurements, so full measurements, then oftentimes the projective measurements are the ideal measurements or the most optimal measurements for some task. And this is often related to this fact that the extremal elements of these effect operators are in fact the projections. So, I mean, of course, this here is a set of projections. So again, why is this the case? So let's take an effect operator which is not a projection and show that it is not an extremal point. So A let F be an effect operator which is not a projection. Which is not a projection. So again, we can write F in a diagonal form. And this D here is again a diagonal matrix, D1, D2, maybe finite or infinite sum. And so, because F is an effect operator, all eigenvalues are non-negative and smaller or equal than 1. So 0 is and because I mean, if every eigenvalue would be either 0 or 1, then the operator F would be a projection, because the square of 0 is 0 and the square of 1 is 1. So projections are exactly the Hermitian operators which have eigenvalues just 0 and 1. Just 0 or 1 and nothing else. So since F is not a projection, there exists one eigenvalue which is strictly in between. Since F, no projection, we can, without loss of generality, assume that, for example, D1 is really, I mean, in the interior of the interval between 0 and 1. Good. So how can we now write this operator F as a convex sum of two other effect operators? Does anyone see this? So we would like to show that F with this property is not an extremal point of the set of effect operators. So we need to write it as a non-trivial convex decomposition of two other effect operators. I guess maybe no one wants to say because of the camera, but then I'll just say it. So we have a number between 0 and 1 which is not 0 and not 1. So of course we will interpret this as a probability, or as what I called previously lambda. It's a lambda which is not equal to 0 or not equal to 1. So in effect we would like to write this diagonal matrix as a convex sum of two other diagonal matrices. So one way to do it is so let me write it down again. So U, D1, D2, D3, U dagger. So this is of course equal to yes, so this is equal to D1 times U, and now let's just put a 1 here. D2, D3, we leave all the other eigenvalues the same, plus, and then of course 1 minus this D1, so I mean this is essentially equal to the lambda in our convex decomposition, times U, and now let's place a 0 here and leave everything else the same, D2, D3, I mean, everyone can verify that this is true because D1 times 1 plus 1 minus D1 times 0 is just equal to D1, and D1 times D2 plus 1 minus D1 times D2 is just, I mean, so this is then, we would define this here as an operator F. It's an effect operator because all eigenvalues are again between 0 and 1. It's an operator F1. An effect operator, and this is F2, an effect operator. So we have in fact managed to write F as a non-trivial convex sum. It's non-trivial because D1 and because D1 is not 0 and not 1, as a convex sum of two effect operators. So F is not extremal. Okay, so we have shown that if F is not a projection, it is not extremal. So the extremal, I mean, any extremal point is a projection. So the extremal points are a subset of the projections. Now we have to show that every projection is in fact an extremal point. Is an extremal point. Well, maybe I'll go over this a bit faster. So take a projection P. So let P equal to lambda times F plus 1 minus lambda times G with P a projection and F and G are effects. And lambda is again in the open interval between 0 and 1. So given such a decomposition, we have to now show that F is in fact equal to this projection. Why is this the case? To show that F is equal to the projection. So, because this is a positive semi-definite operator, we know that lambda times F is smaller or equal than P, because lambda times F plus something positive is equal to P, so lambda times F has to be smaller or equal than P. So, this implies, from what we've shown in the last lecture, that F is in fact equal to the projection times F times the projection. So if something is smaller than a projection, then the support of this operator has to be contained in the projection. So this is what we used before. So this means that outside of the support of the projection, the operator F is also 0. So the operator F is non-zero only within the support of the projection. Outside the support of the projection. Now, what about what happens inside the support of the projection? So what about psi with P of psi equal to psi? So we take an eigenvector of the projection, an operator which lies in the support of the projection. Well, let's sandwich this thing here. So let's take the equation star inside of psi. Implies that if we sandwich this, I mean, because it's an equality, it's lambda psi f psi plus. So this is of course equal to 1. If we take a state in the support of the projection. This here is smaller than 1. This is smaller than 1 because, of course, G is smaller than the identity. And this here is also smaller or equal than 1 for the same reason, because f is smaller or equal than the identity. But now, if any one of these numbers would be truly smaller than 1, so either this would be smaller than 1 or this would be smaller than 1, then the expression on the right-hand side would be strictly smaller than 1, because lambda times something which is smaller than 1 plus 1 minus, lambda plus 1 minus lambda is exactly equal to 1. And if one of the multipliers is smaller than 1, then we cannot get to 1. So this in fact implies that this is equal to 1. So this means that the only eigenvalues of f in the support of P are equal to 1. In the support of P. So F agrees with P outside of the support of P, and F agrees with P inside the support of P. So F is equal to P. So far we have talked about the extremal points of the cone of positive semi-definite operators, the extremal points of the state space, the extremal points of the effect operators, and the last example slash quantum mechanical development is the extremal observables. Let me explain what observables are. Because I think we haven't really talked about this yet. Ultimately, we would like to know what the extremal observables are. Observables. So here, everything I've explained was kind of for diagonalizable operators, so operators which really have a discrete spectrum. All of this can be done also for continuous spectrum if you instead of diagonal matrices you take multiplication operators and partitions of unity. But since we haven't introduced all of these tools, I was just talking like for discrete spectrum. All of this also holds for continuous spectrum. So for the observables, I will now assume that we have a discrete outcome set, or maybe even a finite outcome set. So observable. The name that we also use for this is POVM. So this is a positive operator valued measure, just what it will be. So this is a positive operator valued measure. And so this can be defined on a Hilbert space, on a finite dimensional, on a finite outcome set. Zx, so this is any finite Zx, and an observable also, I mean, because it acts on a quantum system, it needs to have an underlying Hilbert space. This underlying Hilbert space. H. So what is this? This is just a collection of effect operators. So unobservable on a finite outcome set with underlying Hilbert space. H is a labeled collection of effect operators. So it's Fx, where x is an element of the set capital X, with normalization condition that the sum over all these operators equals the identity operator. So I guess we have mentioned that we interpret the trace between rho and f of x as the probability for outcome x. If the quantum state was prepared in the state rho and we measure this observable, this POVM. And because of the normalization condition, all of the probabilities add up to 1. So when we will ask for the extremal observables, we will kind of ask for the finest measurements that one can do on a certain quantum system. So the finest measurements with outcome set X. And we will exclude some cases for, well, so I mean, okay, maybe I should go back a step. So one can view these things. So a POVM, let's call it by curly f, is a labeled collection of operators, and one can view this as elements of a linear space. Or what I want to show is that the collection of POVMs, the set of POVMs with a given outcome set is a convex set. So the set of all of these curly f's, this is a convex set. So I mean, in order to say that something is a convex set, these things need to be elements of a linear space. So we need to define how to do scalar multiplication and addition for these things. So what we define is lambda times f plus 1 minus lambda times g. So this is lambda times this collection of operators g indexed by the same set. So we just define this here to be the collection of operators lambda fx plus 1 minus lambda gx. Again, indexed by the same set x. So it's this kind of corresponds to, so f is a measurement, g describes a measurement, and the convex combination also describes a quantum mechanical measurement. One way to implement this measurement is to roll a dice, and with probability lambda we perform the measurement f, with probability 1 minus lambda we perform the measurement g. And this probabilistic measurement is described, corresponds to this POVM here. So the set of POVMs on a fixed outcome set with a given Hilbert space is a linear set, and in particular, it's even a convex set. Because why is it convex? Because all of these operators are bigger or equal than 0. This is preserved by the convex combination smaller or equal than 1. Because they are effect operators, and if each of those POVMs is normalized according to this condition, also the convex combination as defined here is also normalized. Right? So this is a convex set. And asking for the extreme points of this convex set is asking for, for the measurements which cannot be obtained by this rolling a dice procedure. So the extremal points are exactly those measurements which cannot be written in this form unless f is equal to g. So the extremal observables are somehow the finest measurements. The finest measurements. Alright? And I will now explain, like this is the last thing I'm going to explain is that if the measurements, well, so I will argue that if some of the measurement operators are not rank 1, then it's not, for physical reasons, it's not good to consider it as the finest, as a finest measurement. So if F1 is not a rank 1 operator, so this means F1 is not equal to a multiple of a pure state, then the observable curly F should not be considered a finest measurement. Then, for operational reasons, F is not a finest measurement. This is because if F is not a rank 1 operator, because F can be written in this way. So F is equal to some lambda times F1A plus 1 minus lambda F1B, where they have disjoint support. So how do we do this? Again, we write this as U times some diagonal matrix, D1, D2, D3. And if F is not a rank 1 operator, so if two of these elements are non-zero, we can again lump one element in here, one element in here, and write F as a sum of two operators. Well, actually, even without the lambda. So we take the D1 into this operator and all the others into F1b. So we can write F as a sum of two effect operators, right? And now we could define a set X tilde to be the set 1a, 1b, so I mean, we enlarge the original set by one label, and so we have a POVM over this other outcome set X tilde, which is just the POVM F1a, F1b, so these operators which we have defined here, and we leave all the other operators the same. Right? So this is a POVM over a different outcome set, but if we measure this POVM and we obtain some probabilities from that POVM, then we can infer from this the probabilities of our original POVM F by just by just saying that if this outcome occurs or this outcome occurs, we map these two outcomes to the original outcome 1. And F1 is just a sum of these corresponding effect operators, and all of these we map to outcome 2, outcome 3. So this means that this POVM over X is a final measurement. Than the original F. So when we ask for the finest observables, we will only ask for such observables which have rank 1 effect operators. So let me write this down as the last sentence. So for the finest measurements, we will only consider rank 1 POVMs. Because if it's not rank 1, we can find an operational procedure which makes it final. And next time it will be answered, among the POVMs with rank 1 operators, what are the extremal observables in this set? Alright, so thanks for the attention, and if you have questions you should ask now or later.